Okay, so this is our third video on Chapter 3 material for Math 1560 Calc 1 at U of L for fall 2017. This will be the last video covering section 3.1 in the textbook, and in this video we're going to look at how to find global extrema, how to find absolute max and min values. So there are two places where your global max or min could happen. One is if you're dealing with a function on a closed interval, it might happen at one of the endpoints, right? You might be dealing with a function where the graph, it might look something like this, right? And we start here, we end there, and there are a couple of local extreme values in between. There's a local max and there's a local min, but they're not the global max or min. The global max occurs down here at the left end point, or the global min, sorry, is at the left end point down here, and the global max occurs here at the right end point. So you might have an endpoint maximum like this, and if it doesn't occur at an endpoint, well then it's got to happen somewhere in between. And if it happens somewhere in between, the only way it can really take place in between is if it happens at a local max or min. So if I had, so maybe I start here and I end there, I might have something where maybe the graph goes up like this, and then it goes down, and it comes back up, right? And then this local maximum up here is also a global maximum. This local minimum down here is also a local minimum. And so when we're looking for these global max min values, we've got to check two things. We've got to check the critical points, and we've got to check the endpoints. Because remember, these local max min values, this Fermat's theorem from the previous video, tells us that those local extreme values have to occur at critical points. So this gives us a process for finding these global extreme values, right? And we're looking at this in the situation where we have a continuous function on a closed interval, right? Where the extreme value theorem applies. Remember, the extreme value theorem has these two conditions. One is continuity of the function. The other is that the interval has to be closed. If either of these conditions is not met, then you're going to have to be very careful about analyzing things, and there's no guarantee that these values are even going to exist. They might, but there's no guarantee that they do. So how do we find these values? Well, first thing we do, we've got the endpoints. They're handed to us in the question. So we might as well plug those in, see what the value of my function is at the two endpoints, record those numbers. We just put them away, we keep track of them. Once that's done, we calculate the derivative. Why? Because we're looking for the critical points. Remember that the critical points happen wherever the derivative is 0 or undefined. So we're going to look for those. Once we've got the critical points, we calculate the corresponding critical values. So we take our critical points that we found, we plug them back into the function. And be careful here, right? The critical values are calculated using the original function, not the derivative, right? We know what f prime of c is. It's going to be either 0 or undefined. We don't care about that. We care about at that particular point where the derivative is 0, what's the value of the original function. Once we've calculated all those values, we're going to have a list, hopefully a short list, and we look to see which of those numbers is the biggest, which of those is the smallest, and we'll be done. So here's an example to show you how this works. We've got see if I can move that out of the way. There we go. We got our function x plus 4 over x on the closed interval from 1 to 4. Okay, so here's how we would solve this. I'll come back to this this other question in a minute. But so the first thing we do is we calculate the endpoint values. F of 1 is 1 plus 4 over 1. That's 1 plus 4 is 5. And f of 4 is 4 plus 4 over 4. Also 5. Interestingly enough, we get the same value at each endpoint. Okay. Where do we go from here? Well, the next thing we do is we calculate the derivative. What is f prime? f prime, well, the derivative of x is simply 1. And 4 over x, remember that the derivative of 1 over x is x to the minus 1. Power rule says we get minus 1 x to the minus 2, which is minus 1 over x squared. Multiply that by 4 and we have minus 4 over x squared. If we want to know where this derivative is going to be 0, we need to get things over a common denominator. So we multiply this 1 top and bottom by x squared. That gives me x squared minus 4 over x squared. And we factor the numerator. X minus 2, x plus 2 over x squared. So that tells me that f prime of 2 equals 0 and f prime of minus 2 equals 0. And those are our critical numbers. We don't include 0. It's true that f prime is undefined at 0, but 0 is not in the domain of our function, right? 0 is not in this interval from 1 to 4, so I don't care about those. I only care about the ones that are in this interval from 1 to 4. In particular, I don't care about this because minus 2 is not in this interval that I'm interested in. So that gives me only one more value I have to check. I have to check f of 2, right? I've got one critical point. I've got to plug that into my function. So I get 2 plus 4 over 2. So 2 plus 2, I get 4. Okay, so now I've got 3 values to compare, 5, 5, and 4. Which one is the biggest? Well, the biggest number in that list is 5. So the global maximum is 5. And if we want, we could point out that that occurs at 1 and at 4. The global, min is 4, which is equal to f of 2. Okay, so we found the global min, we found the global max. Now, back to this question, can we solve this problem if we were considering the interval from minus 1 to 4? It's a closed interval, right? Well, no, of course we can't, because in that interval we have 0, and f of 0 is not defined. We've got a vertical asymptote at 0, right? So that function is shooting off to plus infinity on the right of that asymptote, minus infinity on the left. So certainly there's no hope of an absolute max or min value if this thing is going off to plus or minus infinity. Okay, we'll look at some more examples in class tomorrow.